All right. So today, to be a little more talk about probability. So obviously, somebody mentioned this the other day. Probability, the likelihood of something happening. Likelihood of something happening. And we talked about the probability of X. This event X is the number of successful outcomes divided by the total number of outcomes. So we already got that down. And again, we have traditionally seen we've traditionally talked about probability in terms of dice and things of this nature, right? Where we know there's a known number on the bottom of outcomes, known outcomes. Whether it's known or whether you can find them, yes, you can compute them divided by these again known, and this is what we've always referred to this as theoretical probability. So how many ways can you get four aces, or no, I don't know, not four aces, that's a bad one, but like how many different ways can this particular thing happen? That is excuse me, that is how many different ways can this thing occur, right? So for instance, let's say you're gonna have 4 kids. That's probably you have 3 girls. Geez, Mr. Groom, the girl could be the one boy could be first, or he could be second, or he could be third, or he could be fourth. That's right, there's 4 ways over how many outcomes? Well, there's 16 total outcomes, so 4/16, or a quarter of the time. And we'll talk more about that, but that's that idea that it's classical. It's classical, sometimes referred to as theoretical probability. This is what should happen over time. Okay, and so when we start moving through those guys, it becomes pretty obvious. We can always work it out. So let's get a 5-card hand of poker here. Yay, West probably get a full house. Well, I'm not sure, but I do know that the denominator is a pretty big number. Okay, I can find that because that's the total number of 5-card hands. Total number of 5-card hands. And then, of course, this, the number of ways, the number of different full houses, right? And then you can just work through that, and then that's it. Now, we've done this. We will do more of this kind of thing, right? That has always been referred to as theoretical or sometimes classical probability, okay? Empirical probability is what we're going to focus most of our time on. From that standpoint of, I'm going to go out and I'm going to collect some data, whether it's a sample, whatever it happens to be, I'm going to get some data, and then I'm going to find, hey, what's the probability that I just saw this happen? Okay, well, there's 250 car wrecks, and 130 of them were by teenage boys. Holy crap, I'm no math teacher, but that's a lot. Okay, that's an empirical probability. It's how many times that thing happened. Okay, and this again just is from data. So when we're doing that pivot table stuff, hey, look, the number of green-eyed girls, and on top it'd be the number of green-eyed girls with freckles. With freckles. Okay? And so if you think about it, it's the probability that you have freckles given that you're a teenager, that you're a green-eyed girl. Right? And so again, that's the idea. But again, you just go look at the data, figure it out from the data. And then of course later on we'll be talking about experimental probability over time. A couple different ways to think about this one. The classic one is always the dart, kind of thing. Boom, 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 boom. And you're such and such percent likely you'd hit that target, right? It could be a variety of other things. It could be actually giving people drugs and seeing if they're getting better or not. That's also experimental probability. What percent of the ones that got the new drug got better? Okay, but that's the classics. Experimental, don't do a ton. We do some of that, but we'll talk about that as we go. Empirical, we do a ton of that. The classical, we don't do really a ton of that, or the theoretical, we don't do a ton of that. We will do some, but we're not going to do a ton of it. Okay. Now, when you think about this, remember the word and always means multiply. and or always means add. Okay, so you think about this, for instance, when I tell you, hey, listen, we have, well, let's do it this way, actually. This will be a fun one. Suppose you go to dinner. There's 15 entrees to choose from. This is a fancy restaurant. This is not Taco Bell. Okay. You get soup or salad. Okay. Of course, if you go the salad route, there's 10 dressings. Of course, there's potato after that. Potato. What kind of potato you want? You have 5 choices for potato. Soup, there's 2 choices. You could have the tomato bisque, perhaps, or you could have the vegetable beef stroganoff or something or whatever. I don't care. And then you can have the bread. Do you want a croissant or do you want French bread or a sourdough? Okay. And then, of course, what do you want to drink? True story. When I was a kid, senior, I got on the prom court. I wasn't real excited about it because, well, I didn't want to go. Didn't really want to go to this thing. And but I was on it, whatever. And so finally got around to asking this one. Well, I asked this one girl. I probably should have just said, no, I'm not going to my prom. I'm going with her because she was a pretty cool girl. But she was on her court at her school. Should have just resigned and gone with her. It'd have been funner. Whatever. But so I asked the other girl, but she was there out of town that weekend. And then anyway, so then finally, some of my friends like, why don't you ask Karen? I'm like, Karen's got a boyfriend. No, good news. She got dumped. I'm like, you guys are cruel. Anyway, it was the week of the prom, but she was out of town, and she wasn't going to be back till Thursday. So Thursday I see her, and my friend's like, have you talked to her yet? I'm like, no, it's 2 p.m. or something. And she's like, well, you got to go talk to her. I'm like, so I go out there, and I'm like, hey, what's up? How's your thing? She's like, fine. Who are you taking to prom? And I go, you, I guess. And then, so that's, yeah, it was a good time. Really exciting there. So we go there, and we're sitting there, and it's the Marcus Whitman restaurant in Walla Walla, Washington. First time I've ever been out with a gal. She wasn't fancy. A gal at a fancy restaurant. There you go. And it took her for freaking ever to order. Like, forever. Over an hour. I was getting so hungry, dude. You don't even know. Okay? Finally, she orders. Okay? I got to think about that night. There's 15 choices. You need an entree and super salad and potato and bread. There's 4 choices for bread and a drink. How many total choices were there? Well, now listen. It's 15 times 10 salad dressings times 5 potato times 4 times 10. This is if she does salad. But I heard salad or soup. So plus 15 times 2 times 5. 4 times 10. So if a guy's doing a calculator routine on his daily bob, boop, boop, that's 15 times 10 times 5 times 40 is, 15 times 10 times 40. So 36,000 choices. I am quite convinced that she was looking at each one of them. I'm quite convinced of it. You with me? I'm quite convinced that what she was doing was, what if I had the steak with the tomato bisque, with the baked potato, with the Diet Pepsi, with the sourdough? No. What if the steak with the tomato bisque, with the baked potato, with the French bread? With the Diet Coke. No. What if I have and she's going through them all? I'm quite convinced of that. Now, me personally, there was maybe 2 choices for the entree that were good. Because I grew up on a farm. I'm not having steak out. Not happening. Okay? Sometimes I have chicken maybe back then. Maybe a pasta dish. Maybe a lasagna. Okay? But maybe there's 2 choices. I'm not a soup guy out for dinner. You know what I mean? So I'm having salad. Guess what? Back then I was a Thousand Island man. That's it. Never anything else. I wouldn't do the Roquefort. No sirree, Bob. Blue cheese is my favorite now. Could not stand that crap back in the day. Potato. Listen, dude. Baked potato. That's all day, every day. Or maybe mash. Maybe 2 choices there. Bread product. Bro, I hate sourdough. I'm not a fan of sourdough, right? It's not my favorite. Maybe I go French. Maybe, whatever. I will not have a biscuit out because I make a better biscuit than everybody else does. That's not happening. So probably one choice there. And back then I was a Mountain Dew guy. So if you look at it, Mr. Groom had 4 choices. That's all. That's it. That's all. That's why it took me about 10 minutes to decide what to have. Maybe. Tops. And that was when I was talking and having an actual discussion with her about something. Okay? So to me, that's the easiest way to go. When I think about it, this is what's referred to as the first, or sometimes referred to as the fundamental counting principle. Fundamental counting principle. And all it means is this. This is how I say it, is that you multiply the number of choices at each decision point. All right, let's flip a coin. Oh boy. How many choices are there? 2. What if I flip 6 coins? 6 coins. Well, for the first choice, you got 2. Fun 2. Yes? So there's 2 choices. And what about the second coin? Well, and 2. So 2 times 2. Wait, that's 1, 2, 3, 4 outcomes so far, yes? And then 2 more for the next coin? Wait, that's 8 choices because 2 to the 3rd power. So it's going to be 2 to the 6th. There's going to be 64 outcomes. But Groom, you're not doing the choosing. I didn't say I was. God's doing it. Huh? Fate. Whatever you want to go with, bud, I don't care. All right? Piece of cake. It's easy money. Okay? That's the idea there. Okay? So we'll multiply them out. What if you rolled 2 dice? Well, isn't there 6 on each side? That's right. So 6 times 6, 36 total outcomes on 2 dice. Well, people get weirded out about that. It's not hard. Don't worry about it. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's an AMSR video. Bam. 36 outcomes, dog. There they are, right? So pretty easy, kind of fun, kind of nice, kind of fun to do. Another thing we're going to chat about are what are called mutually exclusive outcomes. Okay, these are things like pregnant, not pregnant. You cannot be one, or you have to be one or the other. You cannot be both. Am I right? Right? Awake or asleep. Now, Mr. Groom, can you be awake and driving? Yes. Can you be asleep and driving? You shouldn't be, but yes. Ergo, not mutually exclusive. Okay? Could you be pregnant and awake? You absolutely could be pregnant and awake. Yes, absolutely. Yes, absolutely. Lots of these things. But if you cannot do it at the same time, problematic. When I was a kid, you either played football or you played soccer. There was no overlap back in my day, by God. And now every year you got somebody that's on, oh, I'm the kicker. I play soccer. Okay, good, I guess. Nice, I guess. But we never overlap back in my day, bud. That's just how it was. Okay, that would be not mutually. Those would be mutually exclusive events back in the day. Anything where you cannot be doing this and this at the same time, mutually exclusive. Now that brings up an interesting point. What are called complementary events. These are 2 events that can happen. Or I'm sorry, there are 2 events that add up to 100% probability. Right? That's the idea of it, probability. So we're going to say probability of X plus the probability of his complement is 100%. Okay? So, hey, the probability that you are stuck in traffic, that you are, well, I don't know, have a long commute, plus the probability that you, wait for it, don't have a long commute. Nice. Have a long commute. Better add up to 100%, right? Or probability that on a dice you get a number less than 5, less than or equal to 5, plus probability that you get a number greater than 5, 100%. Probably the gal is younger than you. Plus, probably the girl is greater than or equal to you, greater than or equal to your age. Again, 100%, right? I will put less than your age. Less than your age. Nice. Those are all complementary events. What's the probability that I would have at least one girl out of 18 kids? Yes. You're going to have 18 children. What's probably get at least one girl? Well, first of all, I think it's pretty good. Because you could have 1 girl, 2 girl, 3 girl, 4 girl, 5 girl, 6 girl, 7 girl, 8 girl. Matter of fact, it's this. If this would make you happy, getting at least 1 girl out of 18 kids, then the only thing that wouldn't make you happy is what? Less than 1 girl. Is that right? Does that make sense? This is less than 1. This is greater than or equal to 1. This is less than 1. What a guy can do, and what we'll do a ton of in this class, is we will actually find the complement, because it's way easier to find this, because there's only one way to do that. And so just 1 minus the probability of 0 is equal to the probability of at least 1. We will do that a ton because it makes our lives so much easier. 1 inch of rain on Sunday. What are you talking about? For real? Are you for real? Oh, that's disgusting. Okay, well, great. Awesome. Nice. So that's exciting. So yes, again, complementary events. They are a big deal. Independent events. Independent events, when you do independent events, it's kind of a big deal. One doesn't affect the other. Now, for instance, okay, so Allison this morning spilled milk all over the kitchen floor at home. She cleaned it up. Whatever, because she's a good kid, whatever. Cleaned it up, whatever, She got to school on time. Everything's fine. Everything's hunky-dory. But I stubbed my toe. I believe that her spilling the milk caused me to stub my toe. Mr. Groom, are you high? Well, no, actually, no, I'm not. Because obviously one does not affect the other. Okay? You get up late for work. And as a result, you understand that the milk is rotten when you get out of the fridge. Wait, what? Huh? Mr. Groom's mother lives 300 miles from here. You know, what's the probability that Mr. Groom is late for work? By the way, it's 0. Late for work, given his mom a toast for breakfast. And you're like, what does that have to do with the price of tea in China? And the answer is nada. You understand? Nada. Because those two things have 0 impact on each other. None. Mr. Groom, what is the probability that I'm late for work given I got up late? Well, I'm sure it's higher, you ding dong. Well, yeah, that has something to do with it. Duh. Mr. Groom, I was out late last night and I'm super tired today. Yeah, that's how that works, dummy. You didn't get enough sleep. Mr. Groom, I have a 3-year-old and a 2-year-old little brothers. And when you go in the bathroom, the toilet is just nasty. Yes, because it's dependent on having little boys in the house. That's 100% correct. Those are what we refer to as dependent events. You with me? Dependent events. When I look at these things, I think to myself, now hold the phone now a minute. Wait a minute. Are you telling me that there's one thing, sometimes there's something that will affect someone else? Yeah, that's the whole point of taking medicine, for instance, right? What is the probability that you get well? Probability that you get well, given you took some medicine. Well, the whole idea is what? It's supposed to be that this is a greater probability than if you just get well by yourself, yes? And if that's true, what does that say about your medicine? It says the medicine works. If it's the same, dude, your medicine is not helping you at all, bro. And by the way, if it makes it worse, that's not medicine, dude. That's poison. Okay. Now, my friend, every year, without exception, I don't even know why we're friends sometimes because of this stuff. But anyways, every year, the sucker goes out And he gets cold in the wintertime. Yeah, he gets cold. Him and his family. I got a cold. Oh, it's brutal. And so he goes to the doctor every year, and they give him something every year. And then he spends the entire week out of work sleeping. And every year he'll say something dumb like this. He's like, "Oh yeah, I was home from work all week. I just laid around and slept all week, and I'm better now." I'm like, "Mm-hmm." Well, I went to the doctor and they gave me some pills, and that's what really made me work. I'm like, "It had nothing to do with you just taking a week off and sleeping all week. It had nothing to do with that." No, it's the pills. But it took a week to cure you with the pills. Well, I mean, in that case, I would say, listen, I don't think the pills help, bud. If you have an infection, infections just don't go away. They just don't go away. So you take some penicillin, bam, kills that. You're done. We're back to normal. Everything goes, right? Those are dependent events. And in fact, in statistics, what we'll spend most of our time doing, especially later on, is we're going to actually show, this is later on, chapter 7, 8, 9, 10, 12, all of them, whatever. We're going to show that this variable does or does not affect this one. Show like how much fertilizer you put on, how many tomato plants, how big your tomato plants grow. Okay, probably, yeah, probably. How much Taco Bell you eat, how often, how much you're gonna use the bathroom the next day. Okay, I don't know. These are very much dependent things. Independent things, there's nothing I can do about it, right? I got up late. Of course, I'm going to run over a nail in my tire. What? Huh? What's that? It doesn't have anything to do with it. Now, you might be one of those people who are like, oh, the glass is 3/4 empty. Okay, so you're one of those people. But that has nothing to do with it, right? When you get out of bed, it has no impact on what you run over on the road. That's ridiculous, okay? It just doesn't, right? You can be like, oh, now my life is over. My boyfriend dumped me. And then, of course, I got a flat tire today. Well, unless he sliced it, that got nothing to do with it, you weirdo. Okay? These things happen. Okay? So maybe just quit being weird. Dependent, independent events. Okay, we already talked about conditional. We're going to spend a little bit more time with that in the coming days because that gets to be pretty exciting. All right. Now, next thing I want to say is we already said that when you hear the word or, you're always going to add. Okay? And so when we do these problems, like check this out. So the probability that you're in the band or you are in auto shop. I don't want to hear there's a crossover. For right now, it looks like there's no crossover. Are you with me, bro? Here's all the school children. These kids don't do anything. Losers. These kids are in the band. All right. These kids are in the shop. Awesome. Hey, what is the probability you get a band kid, band or shop kid? There's one honey over 212 total children, yes? This is because these guys here are mutually exclusive. This is the probability of A plus the probability of B, right? You simply plus them. Okay? This is the probability of A or B. And now a lot of people think, oh, that's easy. It is until you see this thing. Here's the band kids. Here's the auto kids. Nice. And 40 and 10 and 50 and 100 and 210. Different school, obviously, yes. What's probably the person is in band or shop? Well, I feel like there's 60 plus 40 is 100 over 210, yes? Different school, by the way. Don't get all weird out about it. That's right. But Groom, isn't there 50 kids in the auto shop? There sure is. Isn't there 60 kids in the band? There sure is. But if we just did 50 plus 60, we would get 110 because we would have counted these guys twice. You with me? So when I see this picture, I look at that and I go, oh, I see. I see. I can't just add the probability of band, which is equal to 60 over 210. Wait, over 210? Mr. Groom, you buffoon. Over 310, sorry. Over 310 plus the probability of auto shop, auto, which is 50 over 310. I cannot do that because that would be, again, too big. So what I'm counting twice is these guys in the middle. And who are the guys in the middle? The guys in the middle are band and auto, yes? So it's the probability of, in this case, band or shop is equal to the probability of band plus probability of shop minus the probability of band and shop. Okay? This always works. You with me? Because if they were mutually exclusive, how many kids did both appear? None. This part here would be 0, yes? In other words, what is the probability that you are pregnant and not pregnant? 0. You with me? If they're mutually exclusive, they don't overlap. There is 0 there. But if they are not, if they are mutually exclusive, if they're not mutually exclusive, like this guy here, that is, there's an overlap, you have to subtract that off of there. Okay? Now, I will say this. If I had a Venn diagram like this right here, I got this nice little Venn diagram. Isn't that cute? That's just cute, room. Whee. Okay? I wouldn't take 60 plus 50 and then minus 10. I would just go, that's 50 plus 10 plus 40 is 100. You with me? Because I'm not going to count them twice on purpose. Right? By the way, this Venn diagram looks an awful lot like this. Shop, band, boom. Are you with me? Does that make sense? In the shop, there's kids in there. There's a total of 50 kids in the shop. There's 10 here. In the band, there's a total over here of 60. There's 10 in there. You with me? That's the idea of this. Okay, what are the other kids into? I don't know. Speech. Yay. I don't know. Whatever. It doesn't really matter. Choir. Oh, yeah. Okay, whatever. Whatever. There's other stuff in here, right? That adds up to 40 more, right? There's kids over here that add up to 50 more, right? Well, that's the idea of it. This pivot table and a Venn diagram, very similar. In fact, I'm just going to say this while I'm here. Suppose you had metal 4 and auto 4. Actually, let's don't do that. Let's do R and R. Mr. Gill, I want to do R and R and auto 4. Well, you can't. You can't. So it turns out that in a pivot table, they would both run this way or they would both run this way because there's no overlap. Yeah, so you can't be in both classes at the same time. Physically impossible to do that. Okay. Nice. And then I think the last thing I wanted to chat about today was, hey, what if you had A and B are independent? Independent. Whatever. Then the probability of A and B is equal to the probability of A times the probability of B. Okay? Okay. Now, there are some things that you think, oh, I bet, Groom. I bet that it's probably, I bet these things are independent. I bet they don't have anything in common with each other. But you have to be careful sometimes in the real world. Hair color and height, are they related at all? Yeah, a lot of times they are, right? So people from, like China, okay, typically shorter people, typically a lot shorter people over there, okay? Most of them have black hair, dark hair, right? So there is some correlation there, and you're like, wait, I mean, it kind of goes together. That's right. So we'd say those are dependent, right? And a lot of times that'll happen. In our country, maybe that's not so much, right? We're a little more mixed up in terms of, we're kind of a little more mixed up in our country, right? In terms of we have taller people and shorter people. We have everything. It's not just one homogenous style of people in this country, right? So in our country, we're going to have a little bit different setup there. But it's possible. Once in a while, you run into one where you're like, I did not know that would happen, okay? We'll talk more about independent, dependent next week or later this week when we start talking about pivot table stuff. Now, some more. I will say this. If you had a dice, and so I need to get a 6 on the dice and a head on a coin, that's equal to, well, it's 1/6 chance of that and 1/2 choice of that. So 1 in 12 chance. Again, why? Because these guys are independent of each other. Okay. Same with coins. Mr. Groom, suppose I flipped 5 coins. What's the probability that I get all heads? I don't know, but I do know that 2 to the 5th power, which is 32, that's my denominator, 32. You with me? And to get all heads, okay, there's only one way to do that, right? But another way to say that would be to say, well, I need to get a head on the first, and. So there's a 1 in 32 chance of that happening. What's the probability, by the way, that I get at least one head? At least, I'm actually going to do at least one tail. And you're like, but Groom, I don't know. But I feel like that's the same thing as probability of saying greater than or equal to one tail. Well, I don't know that, but I do know the opposite of that. The opposite of that is less than one tail. That's the complement, right? And what is less than 1? Well, you can't get anything between 1 and 0, so really it just means probability that x equals 0 tails. And so this is 1/32. And so the probability that you get at least one tail is 31/32. Okay, that's where we're going to leave that off with today. On Tuesday, tomorrow, we're going to have a in-class assignment. Well, you started in class. You may not finish in class. We're going to have an in-class assignment. You're going to be using pivot tables to answer some questions, very much like we did yesterday or on Friday. Okay? All right.